So in this lecture, we got the word problems. And these are specifically called optimization problems because we're going to find some equation and then find the extrema on it. We're going to find the maximum values. We're going to optimize it, try to get the best value we can. And people write down different strategies on how to go about these. And I think maybe the best way is just to start with a problem and show you how I would build it and show you kind of this strategy that I think will help you along. So here's a problem from my math lab. So we are planning to make an open rectangular box. And it's got these dimensions with some cardboard by cutting some congruent squares from the corners and folding up the sides. So the first thing that's good to do here is to draw a picture. If you can draw a picture of something, a picture will always help your brain along trying to contain all the information. So we have a rectangular box. So here it is. And we're cutting off the corners with equal squares. So the blue is what we're cutting off. And if you look at these flaps here, we can fold them up. And we can create a box that has no top. So it says we're planning to make an open rectangular box. So I think that's a good first step. Good first step is to draw a picture. And one of the things that's helpful about the picture is trying to identify the geometry you have here. Because you're going to want to make relations to math, and hopefully you can do that through maybe some geometry of the picture. So if we look at the picture, we've got the blue are squares, the whites are rectangles here, and then we have our middle rectangle. And so ultimately we can identify those geometric objects. And the next thing we're going to do that's good is to label the information given. So just look at so we have our picture. We're trying to build it up with our information. It tells us we have a box that's an 8 by 15. So let's just put that information on there. An 8 got by 15. And that's all we can do, our information-wise. This part tends to be the pretty tricky step, is we want to label things on our picture, because we can't solve for math if we don't have some variables to solve for. And we have to introduce those into our picture. And so that's what I mean with step here is label everything in this picture. You want to have labels on here so you can figure out what all these geometric figures are. But you want to do it with as few as variables as possible. The more variables you add in here, the more relationships you're going to have to find between them. Now, something that's simple for us is because we're a one variable calculus class, means that the ultimate function here has to be of one variable. And so that's the goal you should have in mind here, is you're always working towards a function of just one variable. And you'll see some multivariable calculus if you get to calculus 3. That's when some really cool stuff will happen. So let's label our picture here. And let's do something common. Say this middle part here is x, the distance of this white part here, because the whole distance of everything is 8. And we'll say the distance of this part is y. And then that whole distance is height is 15. And what this allows us to do is then we can figure out now the blue stuff. And in terms of y, because we know the whole length is 15, but the white part here is y, so 15 minus y will give the blue part. So 15 minus y will give us the blue part, but there's two blue parts and they're equal, so we'll divide by 2. And so we can get the length of that blue part, which is the same as this one down here. And we can do the same for x. So we're labeling things, trying to understand the pieces we have here. So the next good step here is, I got this one pasted here, is with your knowledge then of geometry, of objects and formulas, you want to use any relevant geometric formulas you see here with our labels. So, you're not going to use the formula for a triangle because there's no triangle here, but we're going to have rectangles. And I also say your focus is going to be, though, on what the problem wants. And what does the problem ultimately want here? It wants to know what are the dimensions of the largest volume that we can make. And that's where you need to dig into your brain and pull out a volume formula for a rectangular box. Length times width times height. And then we'll identify this with our variables in our picture. So let's say just L, the length, we'll say that's y. And we'll say W is the x. And then for H, the height, so remember the height of this box will be when these flaps fold up, these outside flaps. And the height of these flaps are 15 minus y over 2 or x minus 8 minus x over 2. And we can use either of those for our height. But remember, our goal here is we want to work this towards one variable because we're one variable calculus. And so I'm going to work towards having the input as x. So I'm just going to say the height here, I'm going to choose the x one. So our height, I'm going to choose our x value. And you see we're getting closer. Our volume, which is ultimately what we're solving for, has x here, x here. We got to get rid of this y though. And that means we need to find some relationship between x and y. And if you can see something there, there's many ways you could actually do it, but one is these blue regions are squares, which means this 15 minus y over 2 would have to equal 8 minus x divided by 2. So these would have to equal because they're representing the same length. And then from that, we can solve for y. And we have our relationship between y and x. And we can plug that in to our volume and then get our final function we're looking for, because we have our volume in terms of one variable now, and we can now do our one variable calculus on that. So the final thing I would add to this list here is that your final equation, what you're working towards, is it having one variable. And you do that by finding relations in your picture and then substituting into that your final equation you're working on. So I have a change in plan here, just because in trying to go through this and show you all the work here through this equation editor is turning out to be very time consuming because there's a lot of work to have to go through here. So I've decided I'm going to have to do that pretty much in steps here and paste things over to try to save some time and not keep it from getting too boring. So here is our volume, and we're just taking it directly from over here. Now the first thing I'd do with this, because we want to get the derivative, is I would just distribute that because it's pretty simple to do and it avoids doing the product rule. And so I'd write it as that, and then we can take the derivative. And so there's a derivative, just doing some power functions there. And now to find the extrema, we'll set this equal to 0 and solve. So I just want to say that we can multiply both sides by 2 and get rid of that. And this quadratic does require the quadratic formula to solve. So again, if you want to check that out all by hand, and if you do all that work, the two solutions you'll get are these two. So these are our critical numbers. We check the derivative for any failures. There's no failures, no division by 0, no square roots. So these are our two critical numbers. And which one is the max and which one is the min? So a new thing I'm going to talk about here, something that's quick we can do, is we can look to the second derivative. So here's the first derivative, and we'll take the derivative again, and here's the second derivative. And that, I was going to distribute to half in here, but I'll just leave it like that. It's the same half from there. And remember, the derivative tells us about concavity. So if you're at the bottom of a hill, then you're in a place that's concave up. And if you're in the bottom of a hill, well, that means you're at a minimum. So our critical numbers, we can test them in the second derivative. If we put our critical number in, and it turns out that we get a positive second derivative, well, that means our critical number is at a point where we have a positive curvature. We have a concave up. And so that means we would be at a minimum. So for instance, if we plug -4, take this -4 here, plug it into the second derivative, we'll get 13. 13 is positive, which means this is concave up. So our function is concave up at this extrema point. Which means then that this must be a local min. Concave up, we're at the bottom of a hill. So our critical number must be a minimum. And then we can do the same test with the other one. So if we plug into 14/3, we'll find that's -13. And that means concave down. And concave down would mean you're at the top of a hill. So that would have to be a local max. And so we can see 14/3 is our candidate here. But we do have to check endpoints. So remember, when looking at global extrema, we do need to consider the endpoints. And let's go back to the original function here. It is a polynomial, and a polynomial has all real numbers. So that's the endpoints for a polynomial. Now this is mathematically speaking. In math, the polynomial accepts all numbers. But surely we can't let x go to infinity for the box. That would mean we'd have some infinite size box here. So this is the mathematical domain. And I'm not quite sure if there's a standard name for this, but I like to call it the practical domain. And that is what is practical for the problem you're doing. What is realistic here? So if we look at x, now realistically, x can't be smaller than 0. How could you cut negative paper? But just reality breaks down. Can't interpret that. Becomes weird and strange. And so there's a failure at 0 with reality there. And we'll say we can equal 0. If x equals 0, that means we're cutting the whole cardboard up into absolutely nothing. Now, how large could x be here in this picture? Well, we surely can't cut less than going beyond 8. In other words, how can x be larger than 8? That means, again, we'd be cutting like negative squares out or something. So if x goes to 8, that would mean we're just cutting nothing then. And so realistically, reality and math are breaking down at 0 and 8 here. And so that's our practical domain. So remember, our mathematical domain is all real numbers. But the numbers that make sense for our problem are really only between 0 and 8. So if we really want to know what are the global extrema, if we recall back to doing global extrema, we have to plug in our endpoints, 0 and 8, into the original function to figure out what the true volume is, as well as our critical numbers. So we have to plug all 4 of those in to the original function and see actually what their outputs are. Now, as you expect, if you plug 0 into the function, you get 0. So if x is 0, that means you're cutting everything up, so there's no volume of a box. And if x is 8, that means it extends all the way to the ends, and so you're cutting nothing. There's no flaps to fold up then. And now you can see 14/3 is our maximum. It's our global extrema within this practical domain. So that allows us then to get all our answers now. So remember, we just solved, going back up here, we solved for x. We figured out x equals 14/3. That's our number. And now that we have x equals 14/3, we can plug that into the y equation that we got here, 7 plus x. And we can figure out what y is. And then we can use one of the h ones, one of the heights, 8 minus x over 2 or 15 minus y over 2, doesn't matter. And you'll get the same number. And that's 15/3. And so if we cut up this cardboard, given these dimensions, that will be the largest volume you could create then. Now, if you don't believe that, you'd have to then test it scientifically by, maybe doing 100 of these and trying different values and then observing the data to see where it peaks at maximum volume. And I'm confident it'll be around these values. Of course, realistically, cardboard has thickness and there's other issues I have to get into technically, but, being simplistic here. The more hardcore stuff comes when you get more hardcore. So let's check out another one. And they call this one the best fencing plan. And we got a rectangular plot of farmland. So drawing the picture, we have a rectangular plot. There it is. It will be bounded on one side by a river. All right, so one of these sides is a river. I'll just make it there. And then the other 3 sides by a fence. So here's our fence. And then the other side is just bound by the river there. And it says you have 18 meters of total wire here. And the goal is to create the largest area you can here, the largest enclosed area. So here's our picture, and we need to start labeling it. So let's look at the information we have here. We have this number 800. Let's try to see what that means. So that's the total wire. And we want to connect that to our picture then. So the total wire is going to be this perimeter. So trying to connect that to something geometric, we'd call that a perimeter. And so that's what this 800 is. It's the perimeter. And now how are we going to get this perimeter? Well, we're going to need to introduce some variables. So let's just call this x, call that y. And that tells us the other side's there, so we don't need any other variables. And now let's focus on what they're asking here. What is the largest area? So again, you're going to connect to something in geometry. This is a rectangle, and you know that area is length times width. And in this case, that would be x times y. Now this area function is what we want to find the largest of, but it's of two variables. And we need to get that to 1. So we need to find a relationship here between x and y so we can get rid of one of these. And that's what the perimeter is for. So we need an equation for the perimeter. If you look at the perimeter, you have an x plus a y plus an x. So the perimeter is 2x plus y. And we know the perimeter is equal to 800 because that's the information given. And then with this, we can solve then for y. And now we can take this and plug it into our area formula to get rid of y. And now we have our area function in terms of one variable. And now we're good to go to do some calculus on it. So the first thing I would do here is take our polynomial here and distribute it. Because in this form over here, you'd have to do a product rule on it. But if we just distribute to x, we don't have to do the product rule. So just some straight derivative patterns there to get a derivative. 800x, 8, 4. And there's our derivative. And we want to find the extrema. So we'll set that equal to 0 and solve. And if we move 4x to the other side, divide by 4. And there's our answer. Now, we are dealing with a polynomial here, so notice the dominant term is -2, so that means this is concave down, if you remember some stuff about quadratics. So since this whole thing is concave down, opens down, we know this is definitely the global maximum. And that's our answer. We would want to choose x to be 200. And if x is 200, we can see what y is. It's 800 minus 2x. And we know what x is. It's 200. So that'd make this 400 here to get us our final answer for y. So there you go. If you ever have a cattle rancher or somebody buy some fence and say, hey, what dimensions should I create to maximize my area here so I can get as much cattle in here as I can? What should those dimensions be? There you go. Let's check out another one. This one's called designing a can, like a soda can. And it says, what are the dimensions of the lightest? Now, lightest here is going to be the least amount of area. I'll talk about that in a moment. An open top, so there's no top. Right circular cylindrical, so it's like a soda can. And we want to hold a volume of 1,000 cubic meters. So the best thing here is to draw a picture. So here's a right circular cylinder. There's no top. And we want to see if we can identify any of the information. What other information is here? Well, they're telling us the volume of this has to be 1,000. So we'll write that down. And we need to label our picture. So here's where we're going to have to dig into your brain on what the how to know the dimensions of a right cylinder. But we need the height. And we would need the radius of the circle. So we've put all our information here. And let's focus on what they're asking for. It wants to know the dimensions of the lightest cylinder. Now, lightest here is going to be the least amount of material. And the material makes up the area of this right cylinder. Now, remember, there's no top. So the area means the bottom circle and this part that wraps around. That will all be composed of some material. And so we want to make it as light as possible, which means the least amount of material. And so we want the area to be as small as possible, while still holding a volume of 1,000 cubic centimeters. So that area. So first off, pi r squared. That's the circular bottom. And then imagine for the sides. Imagine you could take the sides of this can and just peel it off. And if you could peel it off into a rectangle. And if you did that, the height of this rectangle would be h. And the length of it would be 2 pi r. The circumference of a circle. And so 2 pi r, the length of this times h, then is the area of this rectangle. And so that's our area equation. Pi r squared for the bottom, 2 pi r times h for the side material. And again, there's no top. If there was a top, we would just have 2 pi r squared. This is what we're looking to minimize, but it has an r and an h. It's got two variables. We need to get this down to one variable, and we need to figure out then some way to relate r and h. And we can do that through the information given. The volume has to be 1,000. So what is the volume of a right cylinder? Well, it's base times height. The base in this case is a circle, pi r squared, times height. And we know this has to equal 1,000. And this gives us a relationship then between r and h. Now, our area formula has an r squared and an r, but only one h. So it's a little bit simpler here to solve for h. So we just have to make that one substitution. And here it is. So here's our pi r squared at the bottom. Here's our 2 pi r, the circumference of the circle. And then the height of our cylinder is going to be then 1,000 over pi r squared. Let's substitute that in. So the first thing I would do with that is our area function is clean it up. So the pi's will cancel out, some r's will cancel. And then take that derivative. And then once we have the derivative, we're solving for extrema, so we'll set that equal to 0. and then we'll solve that for r. Now you will have to multiply both sides by r squared to get rid of that denominator. You'll end up having a r cubed, which means you'll have to take a cubed root to get your final answer. And that turns out to be about 6.8. So that's our critical number. And let's go back to the original function again up here and look at what its domain would be. So pi r squared, it's a polynomial that accepts all real numbers. However, 2,000 divided by r will have division by 0 at r. When r equals 0. So that means then our domain will be from minus infinity to 0, and then 0 to infinity. And that is our mathematical domain. So what is our practical domain here? Now, practical domains don't always have a exact answer. So for instance, if we look at our cylinder to the right, r, if r goes to 0, well then there's nothing. We would have a cylinder that has no radius to it. So certainly 0 is our lowest limit here. We can't make it have negative r. And then what could we take that to? Well, this is where things would get a little subjective on how you choose this, because hypothetically, we could make r extend forever out. And as we do that, remember the volume has to stay the same. The larger we make r, the wider we make our can, the smaller the height would have to be. So, practically, how big are you going to build this can? We could say miles if we wanted, but, realistically, it's going to be, let's just say a couple meters. So it's about 6 feet. If this is really about a soda can, you're certainly not going to want a soda can that's 12 feet in diameter across. So that's our practical domain, about from 0 to 2. Or actually, I should say it's in centimeters there. So 200 centimeters, about 2 meters. Or that is 2 meters, about 6 feet. And, well, if we can't technically plug 0 into our area function because that has division by 0. But that is blowing up to infinity. So as x goes to 0, remember we're looking for what is the smallest area. So I'm looking at the area function here. As this goes to 0, 2,000 divided by 0 will blow up to infinity. We don't want the largest area. We want the smallest. So 0 is too large, going forever. 200, this 200 will go right here. 200 squared, that's going to be very large. We don't want that either. So our end points here on our domain are both blowing up pretty large, which means then that the point we found must be the minimum, because the left blows up to large, the right blows up to large, which means in between must be a minimum. And then it must be our 6.8. And again, you can always graph A here. Graph it on your calculator or on Desmos. Check out what it looks like. And look at where the extrema are. See if they're located at these points we're finding. So once we have R, then we can take R and plug it into h. So h is 1,000 over pi r squared. And if we do that, it turns out h is the exact same. So if you want to build a right circular cylinder and you want to have it have 1,000 cubic centimeters of volume and you want to make it as light as possible, then the radius and the height should be the same. And that'll get your can of least material. Now, in the real world, there's more to it than that, because in the real world, like a soda can, they curve things to make the can stronger. So again, as you get, depending on, your career choices, as you get deeper into things, you'll start dealing with all the other things they do. So let's check out another one. Those are our two answers for R and H. Both same. So here's one that's a little bit more abstract, but still can have uses. And this one is simply determine the dimensions of the inscribed rectangle here, and we want the maximum area. So now this is just one picture they give. The rectangle could look like this, because that's still inscribed within the area. Or maybe the rectangle could look like that. We want to find the rectangle that has the maximum area. So they already gave a picture here for us. So let's label it. Introduce some variables here. So we'll say the length or the width, whatever you want to call it, of the bottom part here, we'll call that x. And then notice that the height of the box is always coming from the output of the function. So we plug in x, and then the function gives us the height of our box. And we know the area of a rectangle, length times width. And in this case, that's going to be x times the function. And they give us the function. It's e to the minus x. So here is our area for the rectangle in terms of one variable. And so that's what we need to maximize. Let me just put that over here. Here's our function of one variable. We will need a product rule on that. That's what that would look like. There's a common factor we can pull out there. And once we have our derivative, we'll set it equal to 0 to find our critical numbers. Now, solving this does mean a zero product property. So that's where, because we have these two factors, which means you can set the factors each equal to 0. And e to the minus x, that is the function you see here on blue. It's this function. It gets forever closer to 0, but can never output 0. And so that one gives us no solution. While this one will get us x equals 1. It just bothers me there's no space in there. I have to go to the text there, though. There we go. So we have one critical number, x equals 1. So let's check the endpoints. Now this one is a little bit more abstract here. So if we look at our picture, we get x to 0. Now, it's not quite specifically stated here, but we don't want x to go negative, because if we let x move to the left, then the box will surely grow forever, and there will be no maximum area. So in other words, 0 is our bottom limit. And then theoretically, hypothetically, mathematically, we can let x go to infinity here. And that would be our domain here. Now, as x goes to 0, well, the box will be going to 0 area. So that's a minimum, or at least a small value. We want the maximum value. So 0 is surely not it. And if x goes to infinity, that means the height of the box is going to 0. And so again, as x goes to infinity, we're going to be having a smaller and smaller area. We want the maximum area. And between that small and small means our critical number must be then the global maximum. And so what are the dimensions of the box? Well, if x is 1, then the height would be e to the minus 1. So a little bit more abstract on that one there. Trying to squish a rectangle under the curve there. A couple homework problems like that. Check out another one. This one's pretty cool. Got a window. The top is stained glass, tinted glass. Bottom is clear. And it's telling us the window has a rectangular bottom here, a semicircle on the top. The rectangle is of clear glass, whereas the semicircle is tinted glass. And the tinted glass only transmits half the light as the clear glass. So more light comes through the clear glass, cut in half by the tinted. And it says the total perimeter is fixed. So this total distance around the window, that's a fixed number. And it wants us to find the proportions of this window that will admit the most light. And it says neglect the thickness of these the bars of the window here. So what information do we have here? Well, we don't have any numbers here at all. And so we're just going to move right to putting some variables onto our picture. And now notice, by calling this bottom rectangle x, that means the radius of this circle then is x over 2. Cut it in half for the radius there. So this x is given the diameter, but we'll need the radius for the circle there. So now we have some variables here. We can see then what the total perimeter is fixed means. So you know perimeter is the length of this line around here. And we can figure that out because we'd have a y plus an x plus a y and then half a circle. So a circle circumference is 2 pi r. We want half of that, so that's just pi r. And that would be our perimeter. X plus 2y, and then plus half a circumference. And this has to be fixed. So what that means is p is just, it's some number. It's like 10. It's not a variable. It's just some number. 100. Whatever you want it to be. And let's get rid of this r here because we know the radius is x over 2. So I'm just going to substitute that in there for r. So the radius, x divided by 2. And let's take a look at the shapes we have here. So we know the area of a circle, a full circle, is pi r squared. And to get half a circle, we'll just divide by a half. So the area of our half circle is pi r squared divided by half, divided by 2. And again, we know what r is. It's x over 2. So I'll just substitute that in. And then what about the rectangle? Well, you know that that's x times y, the area of a rectangle. And so this is looking pretty good. We have a perimeter, area of the rectangle, area of the half circle. Now the half circle is in terms of one variable, so that's good. The area and perimeter, though, have two variables, so we'll have to do a substitution. So really quick here, just up here, I'm just going to clean this up a little bit because 1/2 squared is a fourth. A fourth times a half will give us an eighth, so we can just clean that up a little bit there. And before we get into the substitution here, let's try to figure out what we're actually substituting in. And that means focus on what exactly are they asking for here. So we want to know what will emit the most light. We want the most light coming in. And it gives us this information here that we have light per area. So I'm just going to write that down. We have light per area. Now, how do we get light from light per area? Well, words work just like numbers. If we want to get light from this, we multiply by area. And then areas cancel, and we'll have light. So words cancel. Remember, a word is just a longer variable name. So what does this mean we're going to do? Well, we don't know what this light per area is. And it's just some number. Just going to call it L. And the area, let's look at the rectangle here. So we have our light per area, which is some value L, times the area. And let's do the rectangle first. That would then give us the light from that rectangle. Let me just scroll up really quick here and grab this. So that would be the light from the rectangle. It's some L value, whatever light per area means, times our area will get us our total light coming out of that. Now, what do we know? So this is for the rectangle. What do we know for the tinted glass? Well, it's telling us the tinted glass only transmits half. Well, okay. Well, if the clear glass transmits L, then half of that is L over 2. And the area of half of this transmission is going through the half circle. And then that would be the light that comes through that half circle. And now our goal here is to find all the light. And we can do that. Let me just grab these two here. We can do that because the total light coming through here will be from the rectangle, and I put T there for tinted glass, but that's the half circle. So the total light coming through all this window, the light coming through the rectangle, plus the light coming through the half circle. And we have equations for that right here. So if we look at that, the light coming through the right rectangle is this some unknown value L times the area of the rectangle, which is x times y, plus the light coming through the half circle, and that's this unknown L over 2 times the area of the half circle, which is 1/8 pi x squared. And so here is our function for total light. And we want to admit the most light. So we want to find the maximum of this function. Now remember, L is some number. X and y, though, are different variables. And so we need to get rid of y. And we can do that with the perimeter. We can use the perimeter to solve for y. So this problem does have a lot of work behind the scenes here. But let me take this y. We're solving for y. So here's just solving for y over here. And let's take our function right here, this total light function, and I'm just going to write it over here. Instead of total light, I'm just going to call that t. And this is also with plugging in y. So I took this value for y, I plugged it in right here, and this is the result. And we can clean that up a little bit by just gathering some factors and stuff. And so that's about the best we can make that look. So this is our function. Again, I want to stress, because I'm doing a lot of work behind the scenes here now, is that this is our function. All I'm doing is plugging in y. So I solve for y from the perimeter, plugged it in. That's this result right here. And now I'm just cleaning it up to make the derivative a little bit easier to do. And there's the derivative. And then to get extrema, we'll set that equal to 0 and solve for x. And that one's not too bad to solve for x. And notice in particular that when you solve this, actually let me copy this. When you solve this for x, what's the first thing you're going to do? Well, you're going to get rid of L divided by 2, which means that unknown L has now become irrelevant in solving for x. And so that's why we didn't care what that number was. Now, how would you know that at the beginning? You wouldn't. But, clearly whoever designed this problem knew that L would eventually drop out. So then solving this, we get our answer for x. Remember, P is whatever perimeter you want to choose. If you want to choose P as 10, plug 10 right there. If you want to choose P as 1,000,000, well, then plug 1,000,000 right there. Whatever P you choose, this will be your answer for x. And so this is then the width of this rectangle. And of course, x divided by 2 is the radius of this circle. Now they do want us to get all parameters here. So now that we have x, how do we get y? Well, we have to use the y equation here again. We'd have to plug in x into here and solve for y. And that's actually quite a bit of algebra to do to get it all cleaned up. And that's what it looks like. So again, plugging x into the perimeter for x, and then we can solve for y and clean it all up, and there's our answer for y. And again, here's P, whatever number you want it to be. And there's our answers. All right, so I got one more here because there's a slightly different style of problem. And what's different about it is it's hard to draw a picture. Can't always draw a picture. Well, maybe you can, depending on how creative you are, I suppose. But let's check out this one. This one says you operate a tour service. So just imagine you have a bus tour service. You know, maybe you're those people, you know, you take people around in Hollywood and you show the people, you know, where all the stars live or something. Just imagine you have a bus tour service. And it's offering these rates. You'll charge $200 per person if you have 50 or less people, actually, if you go on a tour. So if 35 people come on your bus tour, you'll charge them $200 a piece. And you'll do that all the way up to 50 people. However, once you have an additional person above 50, up to a maximum of 80 people, so your bus can only hold a total of 80, we'll say, the rate per person is reduced by $2. So again, if you have 50 people, you'll charge $200. But anything above 50, you'll start giving a rebate of $2. So if you have 51 people, you'll give a $2 rebate, which means you'll charge everybody $198 then. And then finally it says, if we have this fixed cost plus a cost per person, how many people do we want on our bus trip to maximize our profit? So there's a lot of information here. And I like to be just systematic about it when there's a lot of information. And just start with the second line here. So the first one is just our context, our bus, where we have a bus service. So our second line is where the information starts coming in. And we want to figure out how much money do we actually get. So the money that you pull in is called revenue. That's what you pull in. And revenue is price times quantity. So for instance, if you had 50 people at $200 a piece, well, how much money is it? Well, you'd multiply that together. 50 times 200 to get your $10,000. Likewise, if you only had 10 people come on your bus trip, well, that means 10 people at $200 will give you $2,000. So our revenue for the first line here, our revenue is price times quantity. And we can write that as an equation then, R equals P times Q. And that's what we're getting from this first part at least. Okay, we have some revenue here, price times quantity. So let's look at this next line here. We have an additional person above 50, and we're going to need to introduce a variable for that. We need to count how many of these additional people we get above 50. And let's call that X. X is the additional people above 50. Now this maximum of 80 people, this is actually going to be an end point, and that's something we'll look at the end of the problem, because 80 is the max we can have, so that'll be an end point. So what does this last part mean? The rate per person is reduced by $2. So if you have one additional person, that's a $2 reduction. If you have two additional people, well, you'll have a $4 reduction. You get a $2 reduction for each person above 50. So if you have 10 people above 50, so a total of 60 people, well, that you'll have 10 times 2, that'll give you a $20 reduction. And we can write that as just a linear equation, 2 times X. So 2 is our reduction, and X is the number of additional people. So what is our price going to be here? So it's $200, but our price is being reduced by 2x. So that means our price is going to be 200 minus the reduction. So again, if you have 10 people over 50, so x is 10, well, that means you're going to have a minus 20. You're going to be charging $180 per person. And then what about Q, the quantity here? What kind of quantity will this give us? Well, we have 50. Remember, quantity means how many people in total here. So we're going to have 50 plus our additional persons. And so our quantity here is simply 50 plus X. And we're going to plug this in then to our revenue function. And there we go. So our revenue is price times quantity, where X represents additional people above 50. I want to make a quick point here, something that confuses some students sometimes, because they'll ask, well, what if I have only 35 people on my trip? Does that mean X has to be minus 15? And no, X is additional people, and that's always going to be greater than 0. You can't have negative additional people. So what happens here is that this revenue function is only true when X is greater than 0. If you have 50 people or less, you would have to switch to a different revenue function. In that case, remember, if you have less than 50 people, there's no price reduction then. So that means you're just straight up charging $200, and then Q is simply the quantity of people. And in this case, Q would have to be less than 50. So if you were looking to model this perfectly, if you have 50 or less people, you would use this revenue equation. But if you have more than 50 people, you'd have to use this revenue equation. But ultimately for this problem, we just need this one. And the next thing that we need to look at, so that takes care of the second line. And we need to take care of now this final statement here. And now comes the probably most important and basic equation in all of business probably. And that is profit equals revenue minus cost. So revenue, the amount of money you pull in, your cost of doing business, so the money you pull in minus the cost of doing business is the profit you have left over to do with what you want. Profit equals revenue minus cost. And we already figured out the revenue function. Notice it's all in one variable, so it's good to go. And so this last statement is talking about cost. And it says we have a fixed cost. So we'll always have a cost of $6,000. So our bus is really expensive to maintain and fuel each time we go on our trip and show people around to the neighborhood. So we have a flat cost of $6,000 and then $32 for each person that comes along. So that's our quantity. Our quantity is 50 plus X. So we're doing a 32, our price, times the quantity. And then this will be our total cost for doing business. And notice again, it's in terms of one variable, and so it's good to go. And now we'll plug revenue and cost into the profit function, and we will then have a profit function of one variable. And then we can finally answer, how many people does it take to maximize your profit? So let's put that all together. And I'm just going to write over here to the left. I'm going to plug R into the profit, the cost in there. And doing that, we'll get all this. So all I did was straight plug in here. And I did distribute the minus sign there, because it will distribute across the cost since it has multiple terms. And this can, through some more algebra, be all cleaned up to look like that. And notice it's actually just a good old quadratic. The dominant term has a minus sign, so that means this is everywhere concave down, which means the number we get will surely be the global maximum. And so to find where that is, we take the derivative. And once we have the derivative, to find that extrema, we'll just set it equal to 0 and solve. Divide out that 2. And divide by 2 again to get our answer. 17. So if we want to maximize our profit in our bus tour adventure, then we would want a total of 67 people. Now again, it does say we can hold up to a maximum of 80, and this is an endpoint. But again, this is a polynomial, a quadratic that opens down, so this 80 endpoint is surely lower than our global extrema. And that's our answer. So something else that's cool with this you can do once you get into Calc 3 and multivariable calculus is that this price reduction, this $2, we can actually change that to a variable to see how that'll affect things. And that would make our profit of 2 variables, and we'd have to do multivariable calculus on that then. But there's, we can add in more things to this. It does require more powerful math to deal with, but this is just a beginning. If you like modeling things with math, this is just a start. And in closing here, I do want to say I know a challenge with this homework is that I'm not showing all the problems, because I do believe that part of what you're supposed to be learning here is trying to figure this out yourself. So I'm confident I've given you all the tools here in what I've talked about, in meaning that these are things that will be useful for you. And you will have different context problems that may seem different, and they are contextually, but you will be going through a lot of this same type of procedure though. So there it is. Optimization problems, our context problems. We finally at our stage where we can apply some calculus to something realistic. And remember, overall, if you are going to have calculus in your career, that means you're going to be applying calculus to the real world, which means doing word problems. So I have no idea what you're choosing for your career, but if math's going to be part of it, I hope you find some enjoyment in this. Talk to you in the next video.